Hey everyone, welcome back to our fourth lesson for our distance learning. We're going to be looking at chapter 7 or topic 7, lesson 4 today, and we're going to be doing graphing of sine and cosine functions. So we're going to start off by checking out our essential question for our lesson today. And you can see our essential question is, how can we identify key features of sine and cosine functions? We're going to look at some new vocabulary today that you guys you've probably seen some of these words before, but maybe not necessarily in a math context. The new vocabulary we're going to look at is the word amplitude, frequency, midline, period, and a periodic function. So let's jump in and do our warm-up for the lesson. All right, the question says, the graph shows a rider's height above the platform when riding a Ferris wheel, t minutes after entering the Ferris wheel car. Part A, sketch a graph of a rider's height if the Ferris wheel is twice as high. How does the graph represent the change in height? So they're telling us that we're going to drag the slider over here, this slider down here, to see the point that we can drag to sketch the graph. So the first thing I want to do is look at this graph that I have right here and just kind of understand what's going on in this picture. So it says that in the problem that that there's a rider on a Ferris wheel. And so you can see down here at time is on our x-axis. When there's been 0 time, that's before the ride has started, when the rider just first gets into the Ferris wheel car. And you can see at this point that this rider, I'm going to actually pop this out so I can see it a little bit bigger. Here we have 0 time. This rider is starting, it's about 2 feet off the ground. So the Ferris wheel car is sitting 2 feet off the ground. And as the car moves, it reaches a maximum height of, let's see, about 22 feet. So we're starting at 2 feet, we're going up to 22 feet. So if I want to go twice as high, well, twice 22 is 44. So I'm going to zoom out a little bit just so I can see everything. And I want to make sure, let's see, I'm going to put the slider on and I'm going to drag this up to a height of 44. And I think that's about 44, but let me zoom in just to make sure. Yeah, that looks right there, about 44. So you can see if the Ferris wheel were twice as high, obviously the graph is going to go twice as high, but it's still starting down here at 2 feet, and it's still getting back to the bottom of the Ferris wheel in the same length of time. The orange graph, it takes 2 minutes to start at the bottom, go up to the top, and then come back to the bottom. And the blue graph starts at 2, comes up to the top, and comes back to the bottom in a period of 2 minutes. It takes 2 minutes to go from the starting point and reach that starting point, that starting point again. So the starting and ending point have the same height on a Ferris wheel. All right, so back here, how does the graph represent the change in height? We could just say the blue graph is twice as high, 44 feet, instead of 22 feet, as the orange graph. And part B of our problem says, sketch a graph of a rider's height if the Ferris wheel is the same height as the first, but it goes twice as fast. So we talked about in part A that you start obviously at 0 time, and it took 2 minutes as we looked at our x graph to get back to the starting point. So if we want to go twice as fast, instead of it taking 2 minutes, we only want it to take 1 minute. So we're going to make this a little bit bigger again, drag this thing over to part B, and you can see that my point is sitting right here. And this time, if you come down to the x-axis, would be like 5 minutes. So what I want is to go twice as fast. So where I am at 5 minutes, I want to cut that in half. I want to cut my time in half if I'm going twice as fast. So if you take 5 and you divide it by 2, that would give you 2.5. So what I'm going to do is I'm going to take this point right here and I'm going to drag it. If this is 3, I want to drag it right here to 2.5. So I'm going to drag it this far over. And I think that's right there at 2.5. And so I realize that looking at this graph, it's very busy. It's hard to see everything that's going on. So I'm going to try to zoom in a little bit and just focus on one small piece of our graph. So I'm looking generally in this area. We can see that all 3 of these graphs start here, basically at the point 0, 2. But in part A, we were looking at the orange graph was the original. So you can see in the orange graph, we go up, we come back down, it took 2 minutes. Well, how fast does it, how long does it take to get back to that starting point if we're going twice as fast? And that's our green graph for part B. So the green graph starts here at 0, 2, it comes up, and then it comes back down. And this point right here where we get back to the starting point should be only 1 minute. So you can see now we're moving twice as fast because the time got cut in half. But another way to think about that is if it took 1 minute to come all the way up and then get back to the starting point, then from minute 1 to minute 2, we can complete another rotation around the Ferris wheel. And so from 0 to 2, for the green graph, we did 2 full rotations, or 2 periods of our graph. Whereas in part A, the orange graph, or the blue graph, because they're both part A, we only did 1 full rotation in 2 minutes. So the green graph, we did 2 rotations in 2 minutes. The orange graph and the blue graph, we did 1 rotation in 2 minutes. So that's how you can show that your graph is moving twice as fast. So how does the graph represent the change in speed? The green graph completes 2 periods, or full rotations, in 2 minutes, while the orange and blue graphs only completed 1 period, or 1 full rotation, in 2 minutes. Okay, so that's our warm-up. We're going to jump now to example 1. And I'm going to stay on this graph. I'm not going to be writing on my screen yet just because there's an illustration that I want you guys to see before I start writing on the graph. Example 1 is about just understanding the graph of a periodic function. So the first thing is, periodic function was one of our vocabulary words, and I haven't really talked about what that means yet. So before we go any farther in example 1, I'm just going to explain what a periodic function is. So periodic just means something that repeats over some length, some period of time. So a periodic function, typically we talk about them as mathematicians, we talk about them as wave functions. If you think about the waves in an ocean, or sound waves, if you guys know anything about music, you've probably seen like frequency graphs of sound waves for the music that you guys make. But a periodic function is just a function that repeats over some length of time. It just repeats, it repeats, it repeats. If you think about the functions that we have talked about already this year in Algebra 2, we've talked about quadratic functions, or parabolas. Parabolas just have some sort of like U shape, but it doesn't repeat. It's just there. It makes a U, and it doesn't make a bunch of U's. It just makes a single U. We've looked at exponential growth functions. They obviously don't repeat. We've looked at natural log functions and regular log functions, and they don't repeat. We've looked at, maybe cube functions or 4th degree functions, but none of those things really repeat because they're not periodic functions. However, in trig, every trig function is a periodic function. So we have sine functions, we have cosine functions, we have tangent functions, and then we have the reciprocals of those. We have cosecant, secant, and cotangent, and all 6 of those things are periodic functions. The basic ones just are sine and cosine, and those are the only 2 that we're going to be looking at today. But as we go, you'll learn more about the other functions. You might not learn a whole lot about them this year, just because the point of doing trig and algebra 2 is just kind of to dip your toe in the water. It's not to get the full experience, but you will definitely get the full experience as you take pre-calculus, and if you ever take calculus, then you'll be expected to know what the graphs of all 6 trig functions look like and how to work with them. So that's what a periodic function is. That was kind of a long explanation. Example 1 says, what is the period of the graph y equals sine x? So the period is just how long it takes a function to start at some value and then get back to that same value, to make a full rotation. So there's a whole lot of words here. I'm kind of going to skip over them for right now. I want to show you this graphic down here that has a unit circle on it. So you can see this unit circle right now. It has an orange point at the point 1, 0. And you know, if this were an angle, this would be a 0-degree angle. You could also think of it as a 360-degree angle if it's a full circle. If we're in radians, then it's 0 radians. And if you make your way all the way around the circle and come back, then it's 2 pi radians. When we're working with trig functions, typically we're going to, and not just working with them, but working with the graphs of them, typically we're going to be working in radians. So we're going to be thinking about pi measurements, starting at 0 radians, and then going pi over 2, pi, 3 pi over 2, and then back to 2 pi. So what I want you to look at is, as we move this orange dot around the circle, the sine, remember, is the y value. It's the height of this point, this orange point, as we move around the circle. And then they're going to be graphing the height as we move around the circle over in this area. And when that's fully graphed, when we move all the way around the circle, that will be a sine graph. So as we start off, we move up, we're moving all the way up, and then we get up to this point. The highest point on our circle is the coordinate point 0, 1, and that's pi over 2. So the maximum of our graph is going to be at pi over 2. And then we keep moving, and you can see the y value is getting smaller and smaller and smaller. And then we get back to sitting on the x-axis. So we're back at 0, and that's an angle of pi. And then we keep on going down, and the y value is lower and lower and lower. And then we get to the lowest point on the circle at 0, -1. And that's a 3 pi over 2 angle. And then we come back, and the y value is getting bigger. It's shrinking. It's getting closer to 0 until we got all the way back to the starting point of a full circle. And so this orange graph right here, this is what a sine graph looks like. So the key features of a sine graph are that at 0, you start at 0. So you have the point 0, 0 on a sine graph. When you get to the top of your circle, that's a pi over 2 angle. Then you're at the point 1. So we have pi over 2, and we're up here at the value of 1. When we make a half circle, we get over here to the angle of pi, and we're back at a y value of 0. So we have pi and 0. When you do 3/4 of a circle, that's a 3 pi over 2 angle, and we're down here at -1. So at 3 pi over 2, we're down at -1. And then when we get all the way back to our starting point, we got to be back at 0, because that's where we started from. And that took us to 2 pi. So a full circle. This is just unraveling the y value of a unit circle and making a graph. And so hopefully you can think about this. If the y value unraveled makes a sine graph, what would make a cosine graph? And we've talked about that before. So I'm just going to kind of leave that question there, not really answer it for you guys right now. But you should be able to figure out what that is. So a period here is how long it takes the graph to make one full rotation. So you can see in this sine graph that we have, one full rotation around a circle is 2 pi. And that's the same for sine and for cosine. We go one full rotation makes the graph. So the basic sine and the basic cosine functions always are going to have a period of 2 pi. All right, let's see what our second part is. Ooh, other key features of a graph. So I'm actually going to jump over and get into editing on my screen now. So we're going to jump over to the other computer. And I need to get this thing to show up. Okay. So part B of example 1, they want to know what are some other features of a sine graph. So I'm actually going to throw a grid on here just so that I can sketch a graph of a sine function and then talk about it with you guys. Let's make this a little bit heavier. Okay, so just like any other graph, you want to start off by drawing your axes. This time, our y-axis and our x-axis. Our x-axis is going to be in radians. So we're going to start off at 0. Let's say this will count as pi over 2. This will be pi. This will be 3 pi over 2. And this will be 2 pi. And I'm going to say this number up here is 1, and this number is -1. So we know that our graph, come on, yellow, for a sine function has to start at 0. When we get to pi over 2, it's going to be up at the maximum. When we get to pi, it's back on the x-axis. When we get to 3 pi over 2, it's down at -1. And we get to 2 pi, then we've returned back to our starting point. So when you sketch your graph, those are the points that you want to make in general. Now you're just going to kind of try to draw a smooth curve, and I'm not perfect at this, but that's the kind of curve that you want to draw. And make sure you put arrow tips on the end, just like you would do on any graph. You always need arrow tips on your end to show that your graph keeps going. This is the graph of y equals sine x. So the key features that we have talked about so far, we've only talked about the period really so far. So we know our period is 2 pi, but in general, the way you can always find, actually before I get into in general, we're going to save that part for example 2, but we know our period is 2 pi. Another feature of our graph is the midline. And the midline is basically, where's the middle? Where's a horizontal line that goes through the middle of our graph? And this one, it might be obvious to you, hopefully it is. The middle of our graph is actually the x-axis. If we highlight over that, you can see that half the graph is above that, half the graph is below that. The midline is always going to be a horizontal line that splits the graph in half. Another feature that we want to talk about that you guys are going to need to know is called the amplitude. The amplitude is how high the graph goes above the middle. So if this is our middle, how high does it go? Or how low does it go below the middle? So we can see that if this is our middle, this is the maximum, that's the highest point, and our minimum is over here, that's the lowest point, and that's a distance of 1. So for this one, we have an amplitude of 1, but in general, the amplitude is how high or low the graph goes relative to the midline. And then some features that we've talked about for all of our graphs this year that we're just going to bring up again. We need to talk about the domain. We need to talk about the range. And we're going to talk about zeros on our graph also. So the domain, hopefully you guys remember by now. Hopefully this is just part of your nature as a mathematician. You just know instinctively what domain is. The domain is your x values that their function touches. And you can see that we're starting at 0 and we go all the way through to 2 pi, but then I drew an arrow tip that shows it keeps going. And on my left end, I drew an arrow tip that shows it keeps going to the left, which means that it keeps going forever to the right and forever to the left, meaning that our x domain goes from -infinity all the way to +infinity. And that's going to be true for every sine and cosine function. It's because it's a wave that's going to just keep on going forever. On the other hand, the range, which you know is the y values, you can see that this function doesn't go forever up. You know, it has a maximum value right here. It has a minimum value right here. So our function has a restriction on the range, and that'll be true of every sine function. It'll be true of every cosine function. For this particular graph, the highest we ever go is +1, and the lowest we ever go is -1. So you can write your range that way. Remember that we use closed brackets, these square brackets. We always use these when we're including the point. We're including this point of 1 over here. We're including this point of -1. So we use closed brackets, but we use open parentheses because you can't, like, infinity is the concept. It's not an actual number. You can't actually include infinity as a number because it's not a number. So anytime you don't include the point, use your regular parentheses. If you are including the point, you need to use your square brackets. And zeros is another topic that we've talked a lot about this year. Zeros happen when the graph is touching the x-axis, and that happens at 0, it happens at pi, and it happens at 2 pi. So we have zeros at 0, pi, and 2 pi. So we have 3 zeros in one period for a sine graph. I'm not sure if you can see that. Let me write that last word, sine, again, a little bit bigger. That's true for a sine graph. So those are the key features that you guys are going to be expected to know and talk about when we're dealing with trig functions. The period, the midline, the amplitude. Probably period and amplitude are the most important things for this lesson, but it's really hard to see the amplitude sometimes if you don't check the midline first. So you're going to need to check the midline to help you in seeing the amplitude. Those are the important new things. Important old things that we've talked about every time we talk about a new function are the domain and the range and the zeros. All right, so let's go on now to example 2. And in example 2, we are going to identify the amplitude and the period of a function. So before we get into this question, I'm just going to give you guys a formula for working with these things in order to identify your amplitude and your period. And here's your formula. Y equals A times, this could either be sine or cosine because those are the two functions that we're going to look at. And then the argument is, oops, didn't want to scroll down. b times x. So that means that we could have one function that says a sine bx, or we could have another function that says a cosine bx. So a is going to stand for the amplitude, and b by itself doesn't mean anything, but 2 pi divided by b is going to be your period. And those are formulas, and you should know them. Well, this a being amplitude is not really a formula, that's more of a definition, but 2 pi over b being your period is a formula, and that's something that you're going to need to know. So what we want to do is analyze the function that we're given and figure out what are the a and b values on this function. So it should be clear to you that 3 at the start of the function is our a value, so we know a is 3. But it might not be super obvious to you what the b is, but realize that b is always going to come after the trig function. You see the b's over here. They come after the word sine or after the word cosine. And so what we have after cosine is just the letter x. But you can always think of just a plain variable as 1 times the variable. So that means for our problem that b is 1. So our amplitude is 3, and the period is 2 pi divided by b, which is 1. 2 pi over 1 is 2 pi. So practically what that means is that the function is going to move, because the amplitude is 3, that it's going to go 3 units above or below the midline. And if the period is 2 pi, that means the graph makes a full rotation in 2 pi units. So the other thing that it's helpful to remember is that amplitude is how high or low you're going. It's a y measurement. And the period is how long it takes you to do something, that it's an x measurement. Okay, so that's part A of example 2. Now let's check out part B of example 2. This time we are looking at the function y equals negative sine of 2x, right in here. Remember that a is the number, or the number that comes in front of the trig function. So in front of the trig function, we just have a negative sign. There's an implication that there's a 1 there. So a might be negative 1, and then b is the number that comes after the trig function. We have 2x there. So b is 2. And so now let's talk about our amplitude and our period. Amplitude is actually always going to be a positive number. So what I should have told you guys is that amplitude is the absolute value of a. So I need to take the absolute value of this and just get 1. But remember that if you have a negative amplitude, it just means the graph got flipped over. So the amplitude is 1. So the graph goes 1 unit above and below the midline. And the period is 2 pi over b. So we would have 2 pi over 2, which is just pi for our function. And I'm just going to show you what this would look like if I graphed it real quick, just because I think it's important for you guys to see what does it look like if we have a sine function or any function that got flipped over. Okay, so I'm going to graph this one in red. We know that sine functions always start at the origin. Oops, before I even go any farther, I want to put some points on here. So this is going to be 0. I'm going to go pi over 2, pi, 3 pi over 2, and then 2 pi. And we know we go up to 1, we go down to -1. So normally on a sine graph, we would be moving up first, but because we have a negative amplitude, we're actually going to go down first. So normally pi over 2 would have a maximum, or the graph of a sine function would have a maximum at pi over 2. But because we're flipping our graph over, instead of it being up there, it's actually going to be down here. And I'm going to erase this. And then we come back to the 0. And at 3 pi over 2, we normally have a minimum. But because we flipped it over, we have a maximum. And then we come back to the origin at 2 pi. So this right here is the basic graph of y equals negative sine of x. So that's just a sine graph that got flipped over. But we don't have just a sine graph that got flipped over. We also have our period changing. We have 2 graphs that fit in one. Our period is just pi, but I went all the way to 2 pi. So I need to be able to sketch an entire graph in just pi units, which means that if I'm going to do this over top of this current graph, what I need is I need to finish at this point pi. Actually, let me do this let me erase that point, and I'm going to finish this in, let's do blue. We're going to finish here at pi. We're going to start here at 0. In the middle of my graph, I'm always going to have a 0. And then halfway between these points, I'm going to have a minimum. And halfway between these points, I'm going to have a maximum. And so my graph would look like this. And so this blue graph is y equals negative sine of 2x. And notice if I kept going with my blue line, I could be able to draw another full rotation before I get to 2 pi, because there's 2 periods in a regular graph compared to a regular sine function. So I do want to point out what x value this is right here. Halfway between 0 and pi over 2 is pi over 4. And then this x value right here is halfway between pi over 2 and pi. And so this point right here is 3 pi over 4. Okay, so that's part B. That's what that looks like. Let's jump now to, actually, I'm going to go backwards to example 2a, because I haven't shown you guys what a cosine graph looks like yet, and I want to do that. So coming back here, I want to graph this function 3 cosine of x. All right, so we're starting at 0. We've got pi over 2, pi, 3 pi over 2, and 2 pi. And I'm also just going to draw over here a really basic unit circle. One change color. Okay, this coordinates of this point right here are 1, 0. Up here, there's 0, 1. Over here, we have -1, 0. Down here, we have 0, -1. So remember, first I'm just going to draw a basic cosine, and then we'll do the 3 cosine x function. Remember that cosine is the x value on the unit circle. So when I start at a 0-degree angle, when I start on the x-axis right here, my x value is 1, which means that I'm going to start at the y value of 1. And then as you move along this circle, when I get to a pi over 2 angle up here, I have an x value now of 0. So at pi over 2, I'm at 0. When I keep moving along the unit circle, when I get to pi, I'm down at -1. And then you keep on moving. You get to 3 pi over 2, you're back at 0. And then as you keep on moving, get back to 2 pi, you're back at a value of 1. So a cosine graph looks kind of like that. You want to try to make smooth curves at the top and the bottom. These points up here should not look like V's. They shouldn't look like that. They should be smooth. So do your best to make them smooth when you're drawing. Okay, so that's what a cosine function is, but let's talk about what this 3 in front of the cosine does. Because that's our amplitude, it's going to stretch our graph to go higher and lower. So if this was 1 and I multiply that by 3, this would be 2, and up here would be 3. If this is -1, then we have -2, and then we have -3. So what a 3 cosine function is would be up here at 3. We stay at 0 because 0 times 3 is still 0. -1 times 3 is -3. 0 times 3 is 0. And then back over here, 1 times 3 is 3. So 3 cosine x is going to look like that. Oops, let's just make my dot bigger. Boom, and then I hit it. So a cosine function, this is what it looks like. It's always going to start at the amplitude value. If your amplitude is 3, it's going to start up here at 3. If you have the red function, the amplitude was just 1, so it starts up at 1. The midline, let's sketch that on here, is still the x-axis. We still show 3 units above or 3 units below. So that's what your cosine function looks like. So let's now move on to example 3. Ooh, before I get into example 3, there is a concept we have to talk about. Frequency, as a concept, is the reciprocal of the period. So I told you guys before that the period is 2 pi over b. Well, if frequency is the reciprocal of that, frequency is going to be b over 2 pi. The concept says y equals sine x and y equals cosine x each have a period of 2 pi and a frequency of 1 over 2 pi, just the reciprocal of that. The function repeats itself 1 time from 0 to 2 pi. Y equals negative sine 2x has a period of pi. We just looked at this function in example 2b. So it has a frequency of 1 over pi, just the reciprocal of that. The function repeats itself only 1 time from 0 to pi, which means that from 0 to 2 pi, it would repeat itself twice. And you can see that in the red graph in this picture here, that it makes 2 full rotations from 0 to 2 pi. One rotation right here to pi, and then we have a second full rotation from pi to 2 pi. Okay, so now that we know frequency, we can talk about example 3. So let's just remind ourselves of this before we get into it. That period is 2 pi over b, and frequency is b over 2 pi. Okay, example 3. What is the frequency of the graph y equals 5 sine 1/2 x? So what I want to do is figure out what is my b value. And remember, b is always the thing that comes after your trig function, the number that's in there. So b is 1/2. And so our frequency is 1/2 over 2 pi. And you might be confused with dealing with a fraction inside of a fraction, but remember, we've talked about compound fractions already this year. The easiest way to deal with this is this 2 is a denominator in the numerator, but you can always put denominators together. So you can put this as 2, this 2 that was in the denominator of the numerator, you can put it down in the overall denominator and just multiply it by the 2 pi that's down there. So 2 times 2 pi is 4 pi, and so your frequency is 1 over 4 pi, which means that the graph makes one full rotation in 4 pi units. So if we were sketching this, if we were making an x-axis, out here it would be 4 pi, halfway of that, the midpoint would be 2 pi, we do 1 pi and 3 pi. Our amplitude is 5, so we're going to go up to 5 and down to -5. And we have a sine graph. So sine starts at 0, then it goes up to its maximum, comes back to the origin, goes down to its minimum, and then comes back to the origin again. And that's what this graph would look like for 5 sine of 1/2 x. Makes one full rotation from the starting point here at the origin and to the ending point at 4 pi, makes one full rotation in 4 pi units. All right, now we're going to check out example 3, part B. This one talks about average rate of change. How does the average rate of change differ within one period of the function y equals 5 sine 1/2 x? Let's first go back, and I'm going to graph this thing again. Let's put up a grid. This will be 0. Let's go with pi, 2 pi, 3 pi, 4 pi. And I'm going to graph this one in purple this time. Oops, let me go back and put my, let's call this, I know this might annoy some of you guys because it's 3 units above, but I'm going to call it 5. And I'm going to call this -5. All right, so we know that a sine graph starts at the origin, then it goes up to its maximum, back to the origin, not the origin, but the x-axis, down to the minimum, and then back to the x-axis. Put some arrow tips on, make it curvy at the top and curvy at the bottom, and put an arrow tip on the end. Okay, so this is what our sine graph looks like, and we want to talk about the average rate of change. The key thing here is you got to remember what rate of change is. Rate of change is slope. So we're going to use our slope formula to talk about rate of change on here. y2 minus y1 over x2 minus x1. So we're just wondering, how does this change within one period of the function? So we have one period goes from 0 to 4 pi. So I think it would be helpful if we made a table of values and we started at 0 and we just used our increments that you can see on the graph. Then we have pi, then we have 2 pi, 3 pi, and 4 pi. And we're going to plot the y values here. At 0, we have a y value of 0. At pi, we're at 5. At 2 pi, we're at 0. At 3 pi, we're at -5. And at 4 pi, we're back at 0. So let's say I looked at the slope between this interval 0 to pi. Well, my slope would be the ending y value, 5, minus the starting y value, over the ending x value, minus the starting x value. And that's going to give me 5 over pi. What if I did from 0 to 2 pi? Well, my ending y value is 0. My starting y value is 0. My ending x value is 2 pi. My starting x value is 0. 0 minus 0 is 0 over 2 pi, which is just 0. If I went from 0 to 3 pi, my ending x value is -5. My starting x value is 0. My ending, oh, sorry, that was y values. My ending x value is 3 pi. My starting x value is 0. -5 minus 0 is -5. 3 pi minus 0 is 3 pi. And I'm not going to do 0 to 4 pi because you can see that we start at 0 and we end at 0. So it's still going to give us an average rate of change of 0 again. Our average slope would be 0. I am going to look at what happens if I start, let's say, from pi to 2 pi. Okay, my ending y value is 0. My starting y value is -5. My ending x value is 2 pi. My starting x value was pi. 0 minus 5 is -5. 2 pi minus 1 pi is pi. So I get -5 over pi. If I did from pi to 3 pi, my ending y value is -5. My starting y value is +5. My ending x value is 3 pi, and my starting x value is pi. -5 minus 5 is -10. 3 pi minus 1 pi is 2 pi. 10 over 2 gives me the same thing that I had before, -5 over pi. I'm not going to do pi to 4 pi because that's going to give me from 5 to 0, which is the same thing as from pi to 2 pi, because pi to 2 pi was also 5 to 0. So I'm not going to bother rewriting pi to 4 pi. There's a whole bunch of different slopes that we can see now. They might not stick out to you, so I'm going to put a box around them in yellow for all of these things. We want to figure out what's the biggest slope that we have here. The biggest one's got to be positive. I only see one positive one, and that's this one. 5 over pi. My biggest negative one is -5 over pi. So this one or this one, because they're the same thing. So how does the average rate of change differ? Let's say the average rate of change goes from -5 over pi to +5 over pi on the interval 0 to 4 pi. So we have the lowest slope that we can see on the interval all the way up to the highest slope that we can see on the interval. An average rate of change, it's just slope. So slope is something that you've known since Algebra 1, but it's also something that can get a lot more detailed and even not more complicated, but just it has more meaning the farther you go in math. And it's actually something that is a pretty big topic in calculus. So all of you who are sophomores who are planning on taking pre-calculus and then calculus will see this concept of average rate of change again in a couple years. But just remember, don't let it freak you out. It's just talking about slope. It's the same slope formula that you've always used, and that's how you're going to be calculating it even when you get to calculus. So that's example 3. Now let's move on to example 4. We've got our word problem, just like we got a word problem every lesson. Example 4, we are going to this time develop a graph and an equation from the description. So we're going to take the words, we're going to pull out meaning from the words that we read on here and come up with an equation for our situation. So the problem says a math teacher has a clock that's centered at the origin of a coordinate system. The hour hand of the clock is 5 inches long, and you can see that in the picture. It's the blue hand. We need to graph the relationship between x in hours and y in inches between the horizontal axis and the tip of the hour hand. Let midnight represent 0 hours and graph the relationship for the time between midnight and 11:59 p.m. Write the equation describing the relationship that you graphed. So we need to think about what's happening to the hour hand if we start at midnight and we go all the way to 11:59 p.m. So I'm going to do up here, let's draw, boom, boom. Let's try to draw a unit circle. We're starting up here at midnight on our hour hand, and we're going to 11:59 p.m., which is basically, a full day. It's 24-hour period. So we want to think about how many times does the hour hand, if it starts here, how long does it take it to get back to this red dot in a full day? So you can see on a clock, obviously we know there's 12 hours, but if we're going from midnight to 11:59 p.m., that's 24 hours. So if we're starting at the 12, we're starting at the top. How many times do I make a full rotation in a day? Well, you guys know how a clock works. You know that you have 2 full rotations in one day. So that means that B is 2. If we think about our period, that's 2 pi divided by B. So we're going to have 2 pi over 2, or just pi. The other thing we've talked about today is amplitude A. Amplitude is how high or low the function goes above the midline. So if we're on a clock, the midline would be the x-axis that I just sketched through the middle. It would be like the 3 to 9 o'clock axis. Because our hour hand is 5 inches long, that means that when we're at midnight, when we're at 12 o'clock, that the hour hand is going to be 5 units above the midline. So our amplitude is 5. And when we're at 6 o'clock, AM or PM, we're going to be 5 units below the midline. So that's our amplitude A. So our general formula we know would be like y equals a times sine, but maybe it's cosine, like we don't really know which one of those it is, of bx. So we know right now that we have 5, and we know that we have 2x in here, but we don't know if it's sine or cosine. So what you need to do is think about, if I'm starting up here at this point above the axis, which graph starts up there? Is it sine or is it cosine? And because we've talked about these already today, and I've showed you the graphs of these, hopefully you guys can remember that it's the cosine graph. So our equation is just going to be 5 cosine of 2x. So that is our equation. But they also want us to graph this because it says describing the relationship that you graphed. I haven't graphed anything yet, so let's graph this. I'm going to jump over to black. I'm going to draw a y-axis and an x-axis. This is going to be 0, and because we make a full rotation in 12 hours, let's do this in hours. So I'm going to go with 12 hours. This will be 6, 9, 3. So this is all going to be my AM, and then I'm going to have 3 p.m., 6 p.m., 9 p.m., 12 p.m. These are my PM hours. But realize it doesn't really make any sense to draw a graph as 3, 6, 9, 12, 3, 6, 9, 12 along your x-axis. That's kind of crazy. So I'm going to translate that into radians. If we have a full circle, we're starting at 0. This would be pi over 2. This would be pi. This would be 3 pi over 2. This would be 2 pi. So I'm going to call this is 0. This is going to be pi over 2. This will be pi. Then we have 3 pi over 2. Then we have 2 pi. But I don't actually want to, like, I'm going to go out and go to, actually, yeah, no, sorry, that's fine. Then if I keep going around my circle, then this will be 5 pi over 2. This will be 6 pi. This will be 7 pi over 2. And this will be 8 pi. Ooh, 4 pi. 4 pi. Actually, I think I messed that up. I definitely messed that up. I'm going to erase all that green stuff. Let's refer back to my period on here. If my period is pi, I know I'm going to make one full rotation in pi. So the first 12-hour period is pi units. The second 12-hour period is another pi unit, so it takes me to 2 pi. 6 p.m. will be half of like 12 p.m. So half of pi, this will be pi over 2. Half of pi over 2 is pi over 4. And then 9 is 3 pi over 4. So essentially what I'm doing is I'm counting by multiples of pi over 4. If I have pi over 4 times 0, I get 0. If I have pi over 4 times 1, then I get pi over 4. If I have pi over 4 times 2, that would give me pi over 2. Pi over 4 times 3 give me 3 pi over 4. Pi over 4 times 4 will give me 4 pi over 4, or just pi. So this next one over here, stop moving around, this will be 5 pi over 4. This will be 6 pi over 4. This will be 7 pi over 4. And then 2 pi is 8 pi over 4. 8 over 4 reduces to 2. I know my graph goes up to 5. This time I'm going to actually make this 5. And 1, 2, 3, 4, 5. This down here will be -5. And then let's sketch our graph. I'm going to sketch this one in blue. I know that the clock starts up here at midnight at 5, that it gets back to 5 after 12 hours, which is pi for us. And then it gets back to there again after 24 hours. In the middle, at 6 p.m., it's going to be down at -5 at 6 a.m. And then 6 p.m., it's also going to be down at -5. And then between the maximum and the minimum, that would be a 3 a.m. and a 9 a.m. and then a 3 p.m. and a 9 p.m. And then I want to sketch this. So we're going to make it curvy at the top. We're going to come through there, curvy at the bottom, go through 9, curvy at the top, come through 3, curvy at the bottom, go through 9, curvy at the top, and then come back down. So there's our graph of this function. And you can see it takes, let me go with purple this time. It makes one full rotation starting at 0, ending at pi. Makes another rotation from pi to 2 pi. So it makes 2 full rotations in a 24-hour period. All right, now let's go to example 5. Example 5 says, the equation for f and the graph of g are given below. This is g. How do the period and the amplitude of the functions compare? So for graph f, let's talk about the period. we know the period is always 2 pi over b, and our b value in here is pi over 4. So we have 2 pi over pi over 4. And to deal with that, I'm going to multiply by the reciprocal, 4 over pi, 4 over pi. So these cancel. The pi over the pi cancels, and we're left with 2 times 4, which is 8. So this makes 1 full rotation in 8 units. That's our period. The amplitude is the a value out in front. It's 4. Then let's look at the g function. So the g function, we can see that the period, we could look at it one way as this is going to be a sine graph because it starts the origin at 0, and then it makes 1 full rotation down, up, back down. Ooh, and then we get back to 0 at 4. So we have the same period of 4. Another way you could think about this is if we are up at the maximum right here at 3, 4, when's the next time we get to a maximum? At 7, 4. How far is it from 3 to 7? It's 4 units. So that shows that that's another way you can see your period. You could also do the minimum to the next minimum. This is at 5 to 9. And that's, you can see again, that's 4 units. So you can see that these two functions have the same period. Let's talk about the amplitude. Wow. I totally screwed that up. These functions do not have the same period. I just went period to amplitude. Period to period, they don't have the same period. The f has a period of 8 and g has a period of 4. And the amplitude of g is how high above or below the axis that we go. So if this is our midline right here through the middle, how far up is this? How far down is this? You can see that these are 4 units above and below, so our amplitude again is 4. They do have the same amplitude. I just didn't draw the arrow to it correctly the first time. So we can say that F and G have the same amplitude, which is 4, but F has a period of 8, while G has a period of 4. All right, so that's example 5. That's the end of the lesson. That's graphing sine and cosine functions. Hopefully you learned a lot. Hopefully you know what amplitude and period are and what the midline is and how those concepts are all related to each other. Remember that frequency is the reciprocal of the period. You just flip the fraction over. And then also you have the ability to talk about the domain and the range of these functions as well as the zeros of these functions. Hopefully you guys are doing well still. I can say I absolutely miss being at school at this point. I'm tired of being at home. I really want to be back in school. In one sense, it's nice only teaching 1 lesson a week. In another sense, I get kind of bored. There's not a whole lot to do. I'm sure you guys are bored too. You probably didn't realize that, school is annoying when you're there every day, but when you don't have it and you just kind of get to sit at home and you can't really do much of anything, you start to kind of miss it. And I'm definitely at that point now. Hopefully you guys are doing well. Have a good week. Work on the 2 assignments that are going to show up with this lesson. And I'll see you guys next week.